Hey everyone, and welcome to today's Explainer. Let's jump right in, because today we're investigating the hidden mechanisms that keep our world running safely. We rely on these massive, intricate technical systems every single day. I'm talking everything from high-speed transit networks to complex power grids. But how often do we actually stop to think about the invisible safety nets, preventing catastrophic failures? Well, today we're lifting the hood. We're going to look directly at the roles of inspection, testing, and system diagnostics. So here's our roadmap for today. 1. The need for dependability. 2. Maintenance testing in action. 3. The power of independent audits. 4. Built-in diagnostic tools. And finally, 5. Data loggers, uncovering truths. All right, let's kick things off with Section 1, the need for dependability. To start, I want you to think about this for a second. How do complex systems actually stay safe? It sounds like a super simple question, right? But the reality is that all real-life mechanical and electrical systems are locked in this constant, never-ending battle against physics. Components inevitably wear down, electrical insulation degrades, parts experience fatigue. Even the most perfectly designed system on Earth is eventually going to degrade over time. The solution here is straightforward but absolutely vital. Maintenance is the process that keeps the system dependable. Basically, this reminds us that these systems are never just a set-it-and-forget-it kind of deal. Dependability requires really proactive interventions. We're talking about preventative maintenance done on a strict schedule, predictive maintenance triggered by smart monitoring, and reactive repairs when things inevitably break down. Without this constant process, the system's safety margin literally just evaporates. Moving right along to Section 2, maintenance testing in action. So, when things are fixed, tweaked, or completely replaced, how do we actually know they're safe to use again? Take a look at the trackside staff here. They aren't just glancing at the equipment, they're actively verifying it. Whenever a piece of equipment is swapped out for a similar unit, or after a really complex repair, maintenance testing is non-negotiable. We can't just cross our fingers and assume a new part works perfectly. We have to definitively prove the equipment is in a safe, reliable state right there on the ground. And this proving process? It's not random at all. It's a highly structured series of engineering steps. First up, we test individual units and hardware, totally in isolation. Then we check their installation and how they integrate with the rest of the puzzle. From there, it's on to safety functional testing, figuring out how the system handles normal operations and, crucially, how it handles failure conditions. Finally, we do commissioning and principles testing, which proves the entire installed setup actually follows the overarching rules of safe operation. The whole thing is comprehensively proven fit for purpose before it ever sees live service. But hey, we've got to acknowledge a really important human element here. Strict test plans are absolutely necessary, sure, but testing after a repair is totally useless if vital steps are just skipped over. Technicians performing these tests actually have to be monitored periodically. Why? Well, because the real-world pressure to get a system back online fast can easily lead to dangerous shortcuts or bad practices. We need that oversight to make sure every single box on the test plan is genuinely checked off. Which brings us to Section 3, the power of independent audits. That begs the question, who watches the maintainers? How do we guarantee these teams are doing it by the book? It all comes down to the psychology between self-checking and independent auditing. If a team just checks its own work, they're super prone to shared misconceptions. They might all make the exact same logical leap, or worse, cave to commercial pressure to just finish the job already. Independent auditing flips the script. The auditor has to be completely independent from the person being audited. That gives us objective verification, totally free from peer pressure or financial influence, which guarantees the safety processes are actually being followed. This kind of independence is the absolute cornerstone of what we call engineering safety management. Now, keep in mind, this is very different from general quality management. Quality management just wants a good product, but engineering safety management is specifically obsessed with catching highly improbable, catastrophic events. It's this massive organizational umbrella demanding rigorous hazard identification, risk assessment, and total independence between the folks building the system and the folks verifying its safety. Okay, let's pivot a bit for Section 4, built-in diagnostic tools. We're shifting gears from human oversight to technological oversight. In high-stakes environments like the heavy machinery you see here, the margin for error is unbelievably thin. We absolutely cannot afford to just wait around for a human operator to notice a failing component or hope it holds out until the next scheduled maintenance cycle. We need real-time fault detection. We need diagnostic facilities baked right into the system itself. Enter condition monitoring. This is a total game changer. By using remote built-in test equipment, we can constantly evaluate the inputs and outputs of a system. Think about it like this. Say we're monitoring the exact amount of electrical current a mechanical arm needs to move. If that current slowly starts creeping up over time, the system identifies that trend and predicts the motor is starting to fail. It instantly alerts technicians so they can swap the item out before it actually breaks. That saves us from dangerous failures and massive delays. Finally, let's look at Section 5, Data Loggers, Uncovering Truths. So, what happens when the absolute worst occurs and a fault somehow slips through all those layers of defense? Well, you can think of these incident recorders as the black boxes of complex infrastructure. Just look at the insane level of detail they capture. They record periodic background scans of inputs and outputs. They log immediate changes of state. They meticulously record every single action an operator or maintainer takes. They even track internal system health and the behavior of connected equipment. It's literally a continuous, time-stamped, unblinking eye. And why bother hoarding all this data? For reconstruction. After an incident, investigators extract this offline data and literally rewind the clock to play back the exact sequence of events. They sift through mountains of information to find the absolute truth, undeniable evidence of where the failure started. Once they find that true root cause, whether it was a mechanical fault, a weird software glitch, or just human error, engineers update the design or the maintenance plan to guarantee that exact same error never happens twice. So, stepping back for a second, what we've really been exploring in this explainer is a unified safety ecosystem. Maintenance testing makes sure repairs are actually sound. Independent audits provide the human governance to enforce the rules. Built-in diagnostic tools give us that proactive technological foresight, and data loggers step in to provide the ultimate retroactive truth. Together, they form this overlapping, ironclad safety net.
I want to leave you with one final thought today. We've seen some incredible advancements in predicting failures using automated tools and remote monitoring, right? But as these diagnostic tools get smarter, faster, and way more autonomous, is independent human oversight, the auditors and the highly trained technicians, still going to be our most vital component in keeping these systems dependable? Think about that for a bit. Thank you so much for joining me on this deep dive. Stay curious, keep learning, and I'll catch you in the next explainer.